Good morning. This is Chapter 2, Programming Language Syntax. Today, we are going to cover the Week 2, Session 1, Chapter 2, Programming Syntax. We will start from Section 2.2 to 2.5. And we actually have two sessions. The first session will cover basically the lexical analysis in this 1.5 hours. And then our Week 2, Session 2, we will be covering the rest of these sections. And that will be more on the parsers. Let's look at the first lecture, Lecture B5. B is Chapter 2. Scanning 1, Lexical Analyzer and the Scanner. As I mentioned before, we have an input program, maybe Java, maybe Python. And then we have regular expression that provide the grammar to the scanner and tokenization to generate the tokens. So we teach you how to use this regular expression to write down your grammar, basically for the token generation purpose. And later, we are going to cover the content-free grammar to model the grammar for a language so that the tokens that generated by the scanner can be converted into a syntax tree. And this syntax tree is used to evaluate the program's validity. And also, it will be used to estimate the syntax correctness and also the type matching for your program. And during this, we also need to generate a simple table, and that simple table is used along the way for the whole program. So this programming language, the first part, we are in Unit 1, and Unit 1 basically covers the structure for a compiler. And the compiler actually can be used in many different applications, such as the AI and any of the application program that require a front stage token processing or tokenization stage. So right here we have calculator language, and this calculator language, it has so many different ID or different operators, and it actually also has some rule that generate the grammars for this calculator language. But theoretically, it's quite a simple language. You basically read in some data, and then you do the arithmetic operations. Right here, let me bring up my whiteboard. And also, I will bring up my pointers. So basically, as I mentioned before, we actually have the regular expression, and that regular expression, you use that to model your pattern. For example, we talk about the integer, and we also talk about the natural number. And natural number, as we say, is actually as the leading 1 to 9, and then followed by these different digits. And that's a natural number. But basically, any input you have, we can consider that as a program, and that actually written in certain language. And then we build a finite state machine to qualify it, and then generate a valid token. And this token actually will basically be a certain pattern like 95, something like that. And we consider this is a token. But a token will be fit into a parser, and the parser will decide this 95 actually is a value, and it actually is a factor, and certain number, it should be a number 95, something like that. So these are the purpose of having this syntax analyzer and the parser. And in this section 2 to section 5, we are basically covering these different topics. So in here, we have this calculator language. And this calculator language basically is in context-free grammar format. And this context-free grammar format can be used to analyze the syntax for the calculator. So first thing is we need to be able to recognize this as a token for a sign and this as a token for minus. And then you should also be able to understand what is a digit and what is a number. And a number basically is a group of digits and dots. So if you generate a 35.75, this is actually one token, and the token need to follow this format. And then the number is maybe used in different places. But so far, this set of the grammar basically is used as mainly for the tokens. So basically, it's a more like a regular language. It's not really in context-free grammar yet, but basically, this kind of language is used for token generation. And later, we will find different way of designing the language for different purpose and for parsers parsing. Let me keep this writer over here. So now let's move on to the next stage. So Schema is responsible for tokenizing the source, removing the comments, and then dealing with the pragmas and saving text of identifier, number, and strings, saving source locations, file number column for error messages. So basically, a scanner is not just providing the tokens, but it also can be used to remove the comments such as this in C or Java, or your punch sign in Python. So those items that's not related to the language you are writing will be removed. And then deal with the pragmas, and usually pragma is used to expand the section of some code in your file. So, and also sometimes it's actually some directive such as include. Those kind of the macros or include statements that actually it is dealt by the preprocessor of C language. And then these two parts, the saving location actually for each string of tokens. It also has the number of the lines, something like that. So this information actually right here is saved in the table. What table? The symbol table. The symbol table we talk about. It actually is saved over here by the symbol table. So during the lexical analysis with the tokenizer such as Flex program, it actually will generate a symbol and put into the symbol table, and also save the line number and even column number for that where the symbol show up in your file. And those kind of data it actually will be kept along the whole compilation stages. And the token you generated will be a simple array or array list or some list of string that can fit into the parser. But parser later will still come back for this symbol table to figure out where these code are, and then maybe work on some checking as well. So that's the scanner's function. Now the next one. The next one is scanning. Suppose we are building a ad hoc. Ad hoc means you just write it the way you want to do, not by a tool. And it's an ad hoc scanner, so you just hard code in it. We read the characters one at a time with look ahead. And look ahead is like before I decided whether there's a certain token of some format, I look ahead one byte or one symbol or a few symbols so that I can decide what is the content for my tokens. And if it is one of these characters, then we basically directly announce it as a token. And if it is a dot, then we need to look ahead for the next character, because the dot may be only a dot, sorry, or it can be two dots for range delimiter, I'm sorry. And let me bring up this pen. So basically, some of the language have this from 1 to 5. Then these two dots and one dot are different. But how can we make difference on this? We basically rely on the look ahead for the tokenization. So when you have the look ahead function, basically you are able to see one more symbol, so that if you have that two dot, you will be able to detect that two dot for the delimiter. Or sometimes, if it is a field selector in some language like Java or object-oriented language, such as using structure in C++, you will be able to basically figure out that there is another ID following the dot. So look ahead to provide some convenience for checking and deciding what are the content for your tokens. So scanning, let me move this smaller. Okay, so I can actually manage my page better. And something like it, maybe. Okay, and then scanning, if it is a less than or angle bracket, we look at the next character, and then if it is a equal sign, then we will announce this angle bracket and then equal sign. Otherwise, we will announce a less than sign. So this one either is a less equal or less. Then we will depend on the look ahead result. But from the syntax analyzer's point of view, I just see an angle bracket and an equal sign, and then I have to interpret it. I interpret the meaning of these symbols at the parser stage, not at the tokenization stage or lexical analyzer stage. And because at this moment we don't have the grammar associated with it. And if it is a letter, we keep reading the letters and digits and maybe underscore until we can no longer. So basically, this actually means, let me show you. Basically, if we will have 5.35 less than equal to B, something like that, if we have comparison like this. So the look ahead will decide what symbol it is. It is a less than or less equal to. And also, if it is a letter or a digit, then we continue to read until we no longer can do that. So that's what this means. And by doing this, you basically generate a token 5.35 and another token less than equal and another token B, and these will be saved in the symbol table and for future use. So it is not involved in the semantical meaning of the symbols or tokens. And this we call basic syntax analysis or lexical analysis. This is called lexical analysis. So you basically only analyze the tokens. And the later stage, we have the syntax analysis in the parser portion. And that portion, actually, sometimes you will feedback data to determine the lexical analyzer as well. So there is actually also a feedback pass that may happen in our compilation stage. It is possible that some of the token, we cannot decide whether it's a token or not, and then we need to have this parser to feedback some data back to the scanner. And also usually it's by the symbol table. So there are two ways. One way is you build the lexical analyzer directly from the regular grammar. The other way is that I based on the context-free grammar, because context-free grammar are in more detail, then I can feedback some information to build lexical analyzer, and then we can do the compiler at one stage using the context-free grammar. So there are several ways of designing this as well. And all of these, we call it the syntax analyzing and analysis. And the front stage, we call it lexical analyzer. Next one. If it is a digit, we keep reading until we find a non-digit. So a non-digit can be a dot, then it's a decimal point. Then we know that it's a break for a sequence of digit, or it actually is a data field selector. And maybe if it is a space, then we start for that. And so basically we keep reading until there's a grammatical segment change. And this is the DFA, deterministic finite automata. And Lex and ScanGen, these are two different generator for the scanner design. So these are two automatic one, and these two are actually systematical software for writing the lexical analyzer. So it's a systematical lexical analyzer generator. These things can be automatic from a set of regular expression to generate. And what we just talked before is actually more with the ad hoc. We are talking about ad hoc. Previously, if we use the one token look ahead scheme to determine the basic information for the tokens. And here we talk about another style. It actually is use the regular expression to build the lexical analyzer, and there are tools like Lex and ScanGen that can help you. So specifically, they construct a machine that accept languages. So the way here we call machine is not really a hardware. It is the finite state machine. And that finite state machine can be a DFA, or it can be an NDFA or NFA, non-deterministic finite automata. Scanners tend to be built three-way. There are three ways. So here we have the summarize. I have a summary. We have an ad hoc scanner builder. We have semi-mechanical pure DFA, and we have table-driven DFA. And typically, people will use either the ad hoc or table-driven DFA. And modern day, I believe the more table-driven DFA will be generated first, and actually it is actually more reliable now because the language become bigger and bigger. But usually people would write a ad hoc program first because it yield faster and more compact code, and you can have the scanner at any stage. But when the language get bigger, and ad hoc will become not easy to manage. So usually they are good automatic generate scanner, and you can use that. And Well, it actually depends. For some project, if your language is not really that huge, then you may use a simple table-driven DFA, and then later you can, if the scenes become very stable, you write your ad hoc scanner to make speed up. But also, if the system really get too big, and then it's hard to manage your synthetical analysis, then you go back to your table driven to build it systematically. So basically, it's hard to say and which way we would end up with, but usually on the project size as well. So here is a ad hoc scanner. So after the scanner return tokens into the parser, when it's invoked, again, it repeats the algorithm beginning using the next available characters of input. So actually, this is somewhat like look ahead, including any that were peak at but not consumed last time. So actually, peak is look ahead and not consumed. As a rule, we accept the longest possible token in each invocation of the scanner. So basically, we keep watching, and then we see some character, and we decided what it is. So basically, a string of character keep coming in. For example, like calculator, we would have 3 plus 4 parentheses times a plus b, something like this. So if we read a parenthesis, then we should do something with the parenthesis. It actually over here, and you will return the corresponding single character item. But if it is actually a digit, then you will go to here. I'm sorry. You will go to here for the digit. So basically, we have a program, and we keep feeding it with some pattern, keep coming, and we saw basically here it's just like a bunch of conditional statement. We see some symbol and we do something. We see some symbol, we do something, and then we modify our status over here. For example, here we need to be able to push in these different items into a stack or something, and then later we be able to analyze what part it is. So that's the function of scanning. Here is the state machine, finite state machine. So basically, this finite state machine can be used for data-driven DFA, and it also is related to this ad hoc scanner. And ad hoc scanner basically is processing those different characters and go to the next step. It basically will handle whatever in this finite automata. And the finite automata basically is implementing the check-in for this set of grammar rule. So here, as we say, this one can be a regular language, and it can be written in regular expression as well. And because regular expression is a subset or easier version of content-free grammar, so basically content-free grammar can also cover all of these as well. But here are the grammar, but we need to develop it into the finite state machine. And finite state machine can be implemented as a table-driven DFA, or it can be implemented as the one we say is the ad hoc scanner. And ad hoc scanner is hard coding. You just write it down in basic a bunch of switch statement or conditional statements. Okay, now let's look at Schema 2. How to convert the regular expression to NFA, non-deterministic finite automata. I'll say right here, we talk about the 3-in-1 feature of the regular expression, regular language, and finite state machine. The regular expression denotes the regular language, and then regular expression can be compiled to a finite state automata, and that we say is the lexical, and this one is actually the lexical lex or flex or skin. Those different tools can help you to convert it to here. And then your regular language will be checked by the finite state machine, and regular expression right to denote the regular expression. That's 3-in-1 feature. And a finite automata have n state. So basically those n state are what? Those n state are just here. It's these different states. And that being described in the finite automata. And that states actually generate from where? From this set of the regular language or regular grammar. And it actually generates this finite state machine. So here, what we want to learn is actually how to generate my automata based on my regular expression. So here is a conversion for regular expression, because we know that regular expression we have optional statement. The optional is a bar, is either A or B. It has concatenation, a symbol followed by another symbol. It has the repetition. These are basic regular expression item. Of course, you can have, and this actually can be written as a BNF, and you can also have the eBNF version for more detailed description for regular expression. But right here, we just cover the BNF part of the regular expression. And this one have the one-to-one mapping to the finite state automata like this. And the grammar would be something like this. If you look at the grammar, it would be something like this. And the grammar to finite automata has one-to-one mapping. So from here is regular expression, you convert to finite automata. And from your grammar, regular grammar, it generates to the finite automata like this. So here is the basic BNF conversion to finite automata. Here is you put into the regular language grammar rule, and then you convert it to finite automata that handle this grammar rule. So either way you put into the regular expression or you put into the grammar format should be fine. And this one later can be extended to Yak or to Bison for parser part. So parser part, you can also write it in context-free grammar and then generate your finite automata. And right here more about flags on the left-hand side, or your lexical analyzer, but you had a regular expression converted to finite automata. So basically, let me draw down something in our whiteboard. Okay, let me clean this. So basically, what happens is that I have a certain file. We have A, B, C, a lot of words, keep typing, right? If then else, whatever. Then this whole thing, we pass through a tokenization. So we read a file. So this can be a file. And then we provide tokenization. And if my program is very dumb, I just read a file and print a file, right? And if I want to do something, I can count the number of the characters, something like that, and then I can label the line numbers. These are the functions that I can actually do. But tokenization is more than that. Tokenization actually break down. I have A and boy, and these are tokens, something like that, right? That's the tokenization. And also, actually, it become a token like this. We've saved into a table. And then we can hardwire analyzing it. Basically, a two part of the analysis. The lexical analyzer, we are working on the inside the token, whether it follows some grammar or not. And then we decided, okay, this is actually a nonce. Or in computer term, it can be an ID. So it update the table in the table. So originally we have A and boy and maybe the line number, some information like that. And later, when I know it is actually a ID, and I put an ID over here, and this is actually another ID, but this one is a quantifier. So we by simple parsing, by simple lexical analysis, by simple analysis, we actually determine. By simple analysis, we actually determine some label A, B, a boy, and then we know that these are some items, and these are done by tokenization. And in terms of interpreting something between them, whether it makes a sentence or not, that part is possible. And then to look into whether that's the token is a valid ID or not, that actually is our lexical analysis. And lexicon is actually a dictionary term. So basically, we are building a table of symbols, and it's actually, you can also think about it as a dictionary of your your language, and then that dictionary later being interpreted between different items or tokens in your token string. I can explore the relationship between these different tokens, and that's how we call it parsing, to analyze the lexical contents. The grammatical contents of that language. So here we have two different things to convert from regular expression to automata, and then from regular grammar set to finite automata. Now, how to generate a finite automata? 3 steps to convert from regular expression to do DFA. First step, convert a regular expression into NFA or NDFA. Actually, these two terms are the same, whether you have ND or N, that's the same. Second step, convert the non-deterministic finite automata to deterministic finite automata. And then the last step to minimize it. So 3 steps we need to do. First, RE to NFA, then NFA to DFA. Third stage to optimize, minimize the DFA. Excuse me. Okay, non-deterministic finite automata. What is non-deterministic finite automata? It is a finite automata, but it actually, for a given input, is never more than one possible outgoing transition is called DFA. So NFA means that you may have one more transition. So I have a state. My outgoing, if I have got 1, I should go to state 2. then this is a DFA. But if there is another one that actually I go to stage 3, then that's a NDFA or NFA. So basically, they are so-called epsilon transitions, arrows label but empty symbol. So basically, they is also can accept the empty symbol as the input. And so it actually had two major features. Number one, a state may have more than one outgoing arrow going to different state, but of the same input. And they might also be an epsilon transition that actually you don't accept any input, but you go into different states. So that's an epsilon transition. So both of these, if you have one of these, then it is a NFA. And if you don't have these, it's a DFA. Now, constructing an NFA for a given regular expression, the trivial regular expression consists of single character C is equivalent to a two-stage NFA, and it's illustrated in figure 2.7. That's next slide. So basically, for example, we have this for the digit, where these are, actually this statement. So we have decimal value, and it's defined by such a grammar. And then we have D star, so D repeat itself. So when we have D repeat itself, then we have a clean closure. So basically, when we saw this part, we can directly jump to here to find its NFA. And we have optional, then it's actually alternative is actually right here. And to concatenation, we actually will build into such a format. So basically, based on the base case, concatenation, optional, and then clean star for repetition, you can have a direct one-to-one mapping from your grammar rule to your NFA. Any of these. So the conversion for this first step is not really hard. It's actually a simple conversion of text string to graph. The next one, NFA representation. So if we have a circle that is one vertex or one state, and then we have two circles that is the end of the program or the end of the terminal, actually is the end state. And besides that, you have different edge that actually is the arrow. It's directional arrow, so you transit from start to the end, and then they will accept certain input, and the input will be put on the edge. And the input for NFA actually sometimes is empty epsilon. So something like this, we can convert basically from here to here. So these are the different conversion states for it. And eventually, this whole thing will be converted to here. So it has an explanation of which part being converted to where. So like here, you have the optional. So this simple part is interpreted here. And actually, this one is the clean star. We have a clean star over here. Something like that. And eventually, you will end up with this. Scanning 3, we will convert from NFA to DFA. So from NFA to DFA is actually a grouping operation. So NFA to DFA conversion. two are equivalent if you accept the same input language and then you provide the same output result. Then actually we can say that these two are equivalent. So basically, as long as the NFA and DFA accept the same input language, whatever makes sense or valid in the NFA, it will also be valid in DFA. Then we actually call this these two languages are the same. So basically, vice versa, if anything generated by DFA, it is also accepted by NFA. Back and forth, we call these two languages are the same. And the two DFA and NFA are actually equivalent. Now, from NFA to DFA conversion, we can take an input that's an NFA and an output is an equivalent DFA. So here is the conversion step number 2 from NFA to DFA, and there are 6-7 stages that we need to do. First, we need to create a state table from a given NFA, and then create a blank state table under possible input alphabet for those equivalent DFA. Then we mark the start state of the DFA by Q0, same as NFA, and then find out a combination of state for each possible input alphabet. And then each time we generate a new DFA under the input alphabet column, and we have to apply step 4 again, so go back to step 4. Otherwise, go to step 6, and if it's done, you go to step 6. The states which contains any of the final states of the NFA are the final state of the equivalent DFA. Okay, this one actually is the guideline, and let's look at the example. So, for example, we have this language accepted by NFA. So the NFA state machine is written down by this. So if we have state 1, state 1 can accept A or B. So for A, we go to state 1, but for B, we may go to state 1 and state 2. And for state 2, we can accept A, that will go to 3, that is the final state. And then we may also accept B and go to final state. But state 3 will go nowhere. So this is the description of state transition table for the NFA. And then we will convert it from here to the target DFA. So first, let's generate a new state called A state. And that A state is equivalent to state 1. So basically, we will copy this over to here, but we will glue it together, so we will actually generate another state called this 1 and 2 as the B state. And actually this B state, from 1 and 2, I get A, 1 and 2, I get A, I'll go to 1 and 3, so I put 1 and 3 here. From B, state 1 and 2, I get B, I will go to 1, 2, and 3. And then after that, actually I put this and this over here. And apparently, because there is a state 3, so we put the new state C and D for DFA. That would be also a final state as well. And then from here, you get input A and B, 1 and 3. I get 1 and nothing. B, I get 1, 2, and nothing. Same for D. So this one actually is a, this one actually is a B, and then this one is a C, this one is a D. So with that, we can actually generate a state transition table for DFA is like this, and the DFA finite state machine is like this. So that actually show you the steps for converting from a non-deterministic finite state machine to deterministic finite state machine. So basically, create a state table. Create a state table means this for NFA. Step 2, create a blank state for DFA. So step 2 is to create, let me see, right here. Let me bring up previous page. So it should be from here, and then you start it to get an empty table for DFA. That's actually our step 2, and then mark the start state for DFA by Q0. So step 3 is just like we just shown here. And step 4, find out the combination of these and possible and create a new state. So 4 and 5 actually are here and here. You start to group different state together. And then we repeat this, and it will generate the whole table. So we are up to here. We repeat it. And then we come. The state 6 will be here to generate a new state transition table for deterministic finite automata. So this we converted from a non-deterministic finite automata to deterministic finite automata. So the idea is from this grammar and transition diagram, we actually can have one-to-one mapping for from the regular expression language, the grammar to finite automata. And then we use the step to convert the regular expression to non-deterministic finite automata. And once you have that, you draw down the transition table. And then we can convert it to a DFA. So the final result by D will be like this. Now, if my chart with epsilon, how can I handle it? It is similar but a little bit more complicated. If I have the epsilon, the empty string, let's say, I have state 1, I may get A, B, C, and may get epsilon, and epsilon is actually a clean closure, so it's just one or multiple epsilon. So you need to follow the transition. So if I get A, I go to stage 2. I get B, I get nowhere for stage 1. And I get C, I go to stage 4. And if I get epsilon, I will go to itself. This actually itself is always a option for epsilon string. Or I may get that's what I have for the state transition for state 1. For state 2, if I get A, I get nowhere. If I get B, I go to 3. Get C, I go nowhere. Get empty string, I may go to 1 or itself. So the yellow one you need to fill in by yourself for a self state, because it usually has the empty string with that. And then stage 3, again, you can find out, go back to 2 for A, and then stay on itself with epsilon. That's it for stage 3. And stage 3 is our final state or termination state. And then number 4, stage 4, we will only accept C to go to stage 3. And then actually for empty string, we got this. So similarly, we put a new A state and put 1 for NFA here. And then we actually start from here to here A and the A empty string, we can go to 1 and 2. B and B empty string, we go to is now nowhere. And C and the C, we go to 4 and 3. Because the empty string, you will directly go 4 and you will go C will go 3. So A, you will go 2, but 2 will, with empty string, you will go 2 and 1. So by this, you go 2 and 2 will go 2 and 1. And B, you go nowhere. C, actually, you go 4 and 4 can go to with empty string, you go to 4 and 3. And then you generate for the B state. You put in this thing into B state and this into C state. Similar to from those without epsilon H. And then here with state 2 and 1, I may go to the sum of these states will be 2 and 1. With B, I go to 3, and then 3 go where? 3 with B go nowhere. And then for C, 2 and 1 for C, I may go to 4, and 4 will end up with this. And if I am 4 and 3, and actually I will be, with A I go to 2, and then 2 maybe go to 2 and 1. And B, I cannot go anywhere. It's a use this. C, I go to stage 3. So let's finish the DFA state transition table. And we can rewrite the state name like this, and we find the deterministic final automata basically with epsilon. So this is quite useful since we know how to convert from RE to NFA, and then now we convert from NFA to DFA. So we finish converting from RE and then to DFA will be like this. But here look like there is some redundancy. We need to do optimization for this. To do optimization for this, we first cut it into 2 parts. Actually is a state with the initial state. Actually those state with not in the final state, and those with in the final state. We put into 2 groups. So the minimization, we start to from a regular expression. And we have now constructed equivalent DFA, right? We started from our RE. And then in DFA have 7 states. A smaller one is this. Now we are trying to do minimization or optimization. In particular, when we have both sides of the D and D star, the only value transition are D, and we ought to be able to do a single final state. We can finalize this intuition, allowing us to apply it to DFA via the inductive construction. So there are certain ways we can do. Initially, we put a state of the DFA into 2 groups, final state and non-final group. So basically, is what I say. Initially, we break it into this and this. So that basically is the grouping of non-final state together, and these are our A, B, C, and this one is our D, E, F, G states. So first we group into here and keep notes of the transition from one group to the other. So like this. And we know that both of these, D and dot and D and dot may repeat itself or go to D, E, F, G. So it's still non-deterministic. And then we try to break it up to avoid the ambiguity. We are able to, when we are unable to find a class to partition in this fashion, and we are done. In our example, the original placement put states D, E, F, G in one class and A, B, C in another, as shown the previous chart. Unfortunately, the start state has ambiguous transition with D and dot because D and dot can go to either repeating the ABC state or will go to D, E, F, G. So we have to break this up so that there is no ambiguity. So we break up C from ABC. It will be something like this. So basically, this is saying to avoid ambiguity, we actually now put those states into AB state and another C state and the D, E, F, G, 3 state. And there's state transition between them. So that's what it is right here. And then the new state AB has cell loop D, and the new state C moved to the state D, E, F, G, and the state AB still have ambiguity on that. However, which we resolve by splitting it into state A and B, as shown at the bottom of the figure. At this point, there is no further ambiguity, and we are left with 4-state DFA. So basically, we create a C state, and then we further split A and B out. So we have A, B, C, and D, E, F, G. So something like from here to here, we try to avoid the ambiguity. So we end up with such a state. Now let's look at this again. Basically, I will make a summary. Basically, we have 3 states to convert from a NFA to DFA. First one, we actually should convert the regular expression to NFA and then NFA to DFA. Final stage to minimize the DFA. So that portion actually, the idea is pretty simple though. The idea is that we initially try to have the real minima state, not only have the start state and the end state. And then we gradually release one state to make sure that the number of state is minimal but not ambiguous. So basically keep the state lean. Don't get too many states. Starting from 2 states, and then gradually we break down a few states out until it can work for us. That is the principle for converting, minimizing the DFA. So we basically convert from NFA to DFA. We have a DFA that contains too many states, but that's fine. When that happens, that's fine. Actually, we will just gradually release one state. We actually break out the C and then break out A and B, and actually just try to avoid the ambiguous. As long as you finish that, and then the grammar and then the finite state machine don't create ambiguity, then that is the minimum DFA that you need. That's the principle that you have. So basically, it's a graph theory problem. You basically convert your NFA to DFA, and then you analyze your DFA by grouping them together, and then gradually release states to build up your minimal DFA. Now let's look at the scanner, and style and pragmas. So scanner's design, scanner code. We can implement a scanner that explicitly capture the circle and arrow structure in DFA, either two main way. So here actually talking about how can we write a scanner, and we know it is ad hoc and table driven, two main ways. So implementation one is actually ad hoc, and with ad hoc we basically use what? We use the case switch statement, or we use go to finish that. So it actually a basic state transition by a big case switch statement. And we can also implement a table driven and driver. And this one, if I have to do it in Python, I will use the dictionary structure, and then I have the key and my value pair. Key is input, value for my next state. That can be used as a good table, because dictionary itself is just like a table, and it can be nested dictionary. So it's quite convenient for Python to build this. And scanning, writing a pure DFA as a set of nested case switch statement is a surprising useful technique, and it is used in Perl, Awk, and Seed. Table-driven DFA is what Lex and ScanGen, so that's what is used by the automatic generator for lexical analyzer. So Lex and Flex. For Flex, I have the video taped last year, so you can look at our spring session. We will have the discussion. Spring 2017 session, you will have the you have a video describing this Flex function, and it basically will help you to generate a scanner, and those sample code also included in our course. And then nested generation, nested case state switch statement. So initially I have a stage one, and if I read a character and my current state is one, I will actually recognize different character, and then maybe I generate the next state based on these two combinations. So with that, I will be able to basically get this. I have a state one. That's a state one over here. And then I have a certain input. As input would be my age, current character. And then inside here, I need to put my next state, X, over there. So it becomes a state transition diagram with that case switch statement. So scanner and the look ahead. Identifier, keywords, variable, method name, class name. These are identifiers. In general, upcoming characters that a scanner must examine in order to make decision are known as its look ahead. So we basically look ahead a few symbols, and then we can make decision by picking at certain symbols or tokens. And in the next lecture, we will see similar notion for look ahead token in parsing. But here we are talking about look ahead symbol. One character for look ahead, or two characters for look ahead. And in messier language, a scanner may need to look at arbitrary distance ahead. So some language, one symbol ahead is not enough. Maybe you need 4 or 5 or certain specific distance away. Number 40, scanning. In messier case, you may not be able to get by with the fixed look ahead. For example, this one actually mean different things. One is loop, one is assignment. One is assigned I to with 1.25. The other one is looping. So here we need to remember that we are doing potentially final state and saving enough information so that we can pick up if it's stuck somewhere. So in some case, you may need to pick at more than one character of look ahead in order to know whether to proceed or not. In Pascal, for example, when you have 3 and you will see a dot, and it can be a constant 3.14 and can be a range 3.5, that's the index range 3 to 5. Table-driven is very straightforward. In the preceding subsection, we sketched how control flow, a loop, a nested case switch statement can be used to represent a finite automata. And alternative approach is to represent the automata as data structure, 2-dimension transition table. And as I said, my dictionary can have nested dictionary that can also be a 2-dimensional transition table. So here I have a table-driven automata like this. And then we can actually use this scanner. We read the current state as we set the current state as 1, and I read a character. And every time I get a character, and then I see what age it is, and then we can use the t current state and the character, and then I generate the next state based on that. And it will stop. The machine will start only until the state that you move to is your current state is actually a final state. Then you won't move. Otherwise, you follow the table, and that table is array type. You have the T table, and then you have 2D indexing, current state and character as 2D, and then you use that to form a transition table. So a Java program for a table-driven would be like this. Each time you read in a character, you read in your character, and based on that, you decide whether to move using the token table current state and setting the new state over here. Basically, you based on the table, and if there is an error, not allow or recognize, you do something else. And recognize is to fix uncertain result. So that's the driver program for table-driven scanner. It's different because it has the table, but basically it's also looping to check the Finite State Machine. So it's similar to the Eckhart algorithm, except that you use the table-driven method. And these are the scanner. And this is the table. So basically, this one is the table for table-driven. So we have certain state, for example, state 2, and I get some certain symbol. Then with that symbol, I go to next state. Will be like this. So this one is actually a combination of state and transition of state. Number 47. Number 47 talk about pragmas. Pragmas actually is when we see pragma and the code may be expanded, and that code expanded may also be used for some special purpose. For example, right here we have pragma parallel, that's OMP, that's open message passing standard, and then it will be expanded as a multi-threading programming environment in C plus language. So that is the pragma may be useful in C language or C plus language. You actually expand it to allow the parallelism. And parallelism, we know that is not in basic C plus language. But with that pragma, we have the capability to utilize the open multi-party threading environment, and then actually allow you to do things concurrently. And that is the use of pragma. So pragma is a special mechanism, and then your compiler or preprocessor will deal with it. And with that, we actually be able to enhance or expand the feature of our programming language. And pragma is also processed in this scanning format. So it actually is part of a pre-scanner, and pre-scanner expanded. So later when we do compilation, those things are solved, and that's one of the tasks we need to do, in the scanning stage to handle the pragma. And pragma serve as hint to people, provide the compiler with information about the source program. So the compiler may ignore these in interest of simplicity or in the face of contradictory information. And now we finished the first part for scanning, and we are moving into the parsing. So parsing actually is a core for the compiler. And as I said, our lexical analyzer does a tokenization, analyze the inside each token what is going on. But parser will be looking at the relationship for the symbol among around the in the program in the tokens. And parser actually explore the relationship of that tokens, and then look into the synthetical information for those token string. And basically, parser, as I mentioned before, it can also generate the pattern that allow lexical analyzer to get the right token for the parser. So parser is the heart of typical compiler. It has the symbol table, syntax tree, semantic analysis. So parser calls a scanner to obtain tokens for the input program. So here, parser actually may also feedback to scanner. But this actually depends on what your design of the compiler. But most modern day parser will handle this. And then parser assemble the tokens together into syntax tree and pass the tree to a later phase of compilers, which will perform semantic analysis and code generation. So parser analyze the syntax tree, and that information is used for code optimization and the code generations. So in fact, parser in charge of the entire compilation. The style of the compilation sometimes is referred to as a syntax-directed transition. So here is a complete view of semantic compiler function. So parser is a central part. It generates a syntax tree for the latest stage. It takes over the token string from the previous stage. So parser is the real center of the compiler. So here is one parsing example. We basically read A times 2 plus 1. we can break down into such a tree. And this one is the ALR parsing. And parsing means that we need to analyze the tokens relationship. So A times 2 plus 1 is A times 2 and then plus 1. So it's an example of LR parsing. And terminology, we have the context-free grammar for push-down automata. We have simple, and simple can be terminal and non-terminal. And production dual, that's actually defined in the context-free grammar. And context-free grammar is a little bit more advanced compared to regular grammar. As I mentioned, there is a stack and recursive function, and that means a stack in your software or hardware implementation. And that recursive feature makes context-free grammar more powerful in handling the parsing. So you have a derivative for grammar, and also you have the parse tree as a sentential form. And sentential form, what is sentential form? A sentential form is the star symbol S and O. It's all the things that can be derived from the star symbol. So consider that we have the grammar that is, and this grammar here is the production dual. You have starting symbol, you have the terminal and non-terminal, and then by this dual, you can derive from S with these different patterns, and that patterns is called sentential form. And sentential form is a linear form, and each sentential form has at least one variable, and hence there's never any choice about which variable to expand next. So sentential form can only allow one variable. That's called sentential form. More than that, it is not linear. Parsing. By analog to RE and DFA, context-free grammar is a generator of context-free language, and a parser is a order of N3, and N3 actually is costly operation. So when your number of state or the language get more complicated, then the algorithm will slow down. That's why I told people that the first pass, you can design a table-driven compiler, a parser, but later you have to decide whether you move to hardcore or the what's that, ad hoc coding for the parser or not. So there is an infinite number of grammar for every context-free grammar, context-free language. Not all grammars are created equal. However, there are large classes of grammar for which we can build parsers that run in linear time. So basically, order n cube is not linear. It consumes more time. But if we actually design the grammar in the right way, some of the language we can actually handle nicely, even bring it down to linear time. And parsing, it turned out as for any CFG, we create a parser that is order of n cube. And there's a well-known parsing algorithm that implement that. It's called Early's algorithm and Cook-Yeager and Kasami algorithm. And order n3 n cube time is clearly unacceptable for a parser in a compiler. So it is really too slow. And then parsing style. So the parsing style, we have the LR and LL parsing. LR is left to right, and derivation leftmost, and parsing tree is top down, and then algorithm is predictive. And LR is left to right, we derive from rightmost, and it's a bottom up parsing, and it's based on the algorithm shift and reduce. So LL means top down. LR means reverse or bottom up. So remember that R is reverse. So parsing, LR parsing is also called top-down parsing or predictive target. And LR is bottom up and is also called shift reducer parser. So there are different flavors of LR. One is called simple LR, that's simpler than regular LR1, and also look ahead LR. And look ahead LR actually is a simpler version of the LR parser, but usually is widely used. And then top-down bottom-up parsing will provide different results. So let's look at it. Here I have an example of the ID example. So with this, my parse tree can be like this. If I have ID stuff. So this one we call it LL, means we go L first, and then the tail we match the first row, and the next row would be left to the right. And actually we have match first A first, and then the tail to be matched later. So by doing this, we build a syntax tree like this. And then this one is called LL parsing. And because it is organized that we actually check the first symbol first. And that actually one way to do parsing. The other one is like I do bottom-up evaluation for this LR parsing. So the bottom-up parser begins with noting that the leftmost leaf of the tree is ID. The next leaf is a comma, and the one after that is a ID again. So it's the ID.ID comma ID comma format. But these two actually interpret the grammar in different way. So at no point does the bottom-up parser predict what it will see next, because bottom-up doesn't do prediction, but it do like referencing using the shift and reduce method. So it shift the token into forest until it recognizes on the right-hand side, which it then produce the left-hand side. Because this behavior bottom-up parser are sometimes called L shifting, L actually called shift reduce parsers. And both bottom-up parser were the first to receive useful formal study. Rightmost deviation, sometimes also called canonical. I'm sorry. And building space with bottom-up grammar. This one is a bottom-up grammar, and this is bounding up space. So we have different way of handling it. It's a bounding space. So we basically let it be bound up with the comma on the left. So the previous one, we have one same grammar, but we interpreted with LR parser and LL parser, it will end up with different grammar. And here it is a different way of constructing the grammar. If we write it in different way, we can be using the bounding space for a bottom-up grammar. And parsing, every LL1 grammar is also a LR1 grammar. The rhyme recursion in production tend to require a very deep stack and complicated syntax semantic analysis. Every context-free language that can be parsed deterministically has a SLR1 grammar, which is LR1. Every deterministic CFL with prefix property has a LR0 grammar. So parsing LR1, LR parsing with one token look ahead. So if you see LL1 or LR1, that number indicates how many tokens of look ahead are required. So basically it's the degree of look ahead. Almost all real compilers use one token look ahead. The expression grammar you saw before is LR1, not LL1. So this one has the left recursion. So it's not a LL grammar. And here are the summary for type of parsing. You have top-down parsing and bottom-up parsing. And for top-down, you have recursive descent. Get parsing and then has the non-backtracking feature, and then predictive parser that will form a LL parser. And then bottom-up, this part is LR parser family. So today we will stop over here and hope you enjoy the video, and we will come back on Thursday for week 2 sessions 2. If you have any question, let me know. Bye now.